Hello. Today I'm going to talk to you about yet another way to find the potential or the electric field. We are going to use Laplace's equation, starting from Poisson's equation. All right, so what do we know? Well, we know Gauss's law, written in differential form, looks like the divergence of E equal to the charge density over epsilon naught. But we also know the following. We know that the potential is equal to, we know that the electric field is equal to the minus the gradient of the potential. So we can take this and plug it in to that equation. When we do, we get the following. Bring the negative on the other side of the equation. Well, this del dot del is the Laplacian. So we get this wonderful equation here, which is the Laplacian of V is equal to minus the charge density over epsilon naught. Okay, so at first this seems like, this just looks like another equation we have to memorize. But we really can think about how powerful this is, because in many situations, the charge density is 0, right? You have nothing there, empty space. The charge density is 0. And so this reduces down to the Laplacian, right? And this is an equation that we're experts on solving, because we have to solve this in a variety of different parts of physics. So we can just use the skills that we've learned. Now, probably many of you, this will be the first time that you really dived into solving this differential equation. But it's one that will pop up over and over and over again. So I suggest that you become an expert on it as soon as possible. Don't worry, we're going to spend a good week or two just solving problems with this. So this is a differential equation. And you know that if I have a differential equation, if I have a solution to the differential equation that matches the boundary conditions, then it's a solution, no matter how I found it. So I'm going to want to have to find something called the boundary conditions. Okay, let's dive into that in a little bit more detail. What do I mean by boundary conditions? Well, let's take a look at one boundary condition. The potential is continuous across a boundary. Potential is continuous across a boundary. So if I have a surface here, and I know that there's some point here on my surface, my boundary, right? We'll call this point A, right? The potential outside has to equal the potential inside at that point A. So potential outside A vector has to equal potential inside A vector. So why? Well, there are a few different ways to prove this. The way that I like to prove it is to look at the integral. How is the potential defined? Well, the potential, right, delta V is equal to minus the integral E dot dl. Okay? So what I'm going to do is I'm going to look at 2 points. I'm going to say V outside, and we're going to call this A plus, because we're going to approach it from the outside. Let's say A0, that probably makes more sense. Minus V0, approaching it from the inside, right? Approaching that point, is got to be equal to minus A inside to A outside, which is just the size of this boundary. Basically, I'm doing the integral from A to A, right, of E dn, right, the E across that boundary. Now, I can think about integrals. So I already know that the integral of 1 to 1 of x squared dx is equal to 0. Right, let's do that integral. X cubed over 3, right, and then I take the 1 and I put it in here. You get 1 over 3, and then I take minus, and I take this 1 and I put it in, and I get a minus 1/3. This, of course, works out to 0. In fact, that's a relationship that you need to know about integrals. That in general, if I have the integral from A to A of f of x dx, this is going to be 0 as long as f is well behaved. So, what's an example of a function that wouldn't be well behaved? Imagine if I had a delta function, right, that went to infinity at point x. That would be a problem. But the electric field really refers to a force. Is there a time ever where the force can be infinite? Let me take a moment and think about that for a moment. Is there ever a time when you can have an infinite force? You can have a very big force, but you're probably not going to have an infinite force. Because if I'm applying a force on something, right, I can't apply an infinite amount, right? I can apply as much as I want. I'm never going to get to infinity. So the electric field is going to be a well-behaved function. So as I squeeze this integral around closer and closer and closer to that boundary, I get a thing where it looks like this, where I'm doing my integral from A to A. Well, I know that if I do my integral from A to A of a well-behaved function, this has to be equal to 0. So that tells me that the change in the potential across that boundary has to be 0, or that the outside potential has to equal the inside potential at that boundary. Okay, so that's the first boundary condition that we need to know about. What's the next one? All right, so the next boundary condition is also very important. So let's go ahead and start with Gauss's law. But now, let's use the integral version, right? The integral of dA of equals, integral of E dot dA is equal to the charge enclosed over epsilon naught. Now imagine I have some charges on the boundary of a surface, right? So this is a boundary It's a boundary layer, and these are some charges that are focused on that surface. No matter how jaggy or curvy or whatever my surface is, I can always go close enough to my surface where I get a nice perfect plane, right? So if I zoom in on that, eventually I'm going to get something that looks like this, a nice perfect plane. And there I can apply Gauss's law, right? I have some charge that's on the surface, and now I can do my normal cylinder that I do whenever I have an infinite surface of charge, right? And so I have my E here, E on the outside, let's say, E2, and then I have my E1, which is on the inside. They may not be equal because there's charge in the middle. But I do know, by looking at Gauss's law, right, that the charge will either go to or away from those charges. So you're going to have E2A minus E1A. Sorry, it's going to be plus, right? Sorry, here it's going to be minus, right? Because here my area points out, here my area points out, here my E points out, but if I'm defining this E as plus, right, that's the plus direction, this area, the E will be negative, right, because the E is going to have to point in the opposite direction, right? So, and that's going to be equal to the charge enclosed over epsilon naught. Okay, so then what we do is we divide this whole equation by area, and you get E2 minus E1 equals Q over area over epsilon naught, or sigma over epsilon naught. Okay, and now we think about how the electric field is connected to the potential. This is really right? It's the gradient of V2 minus the gradient of V1, sorry, and this will be negative because each of these has a negative sign. Okay, so right on this direction is pointing either away or towards the boundary, right? Think about it. If we had our boundary here and we had our charges, and we had drawn our little cylinder here, our Gaussian cylinder, the electric field is going to be pointing away if they're positive charges, or it's going to be pointing toward if they're negative charges. It won't point in any other direction that isn't perpendicular from those surface charges. So when I look at this, this is going to tell me that the normal, right? So this is the n direction, the normal direction to that surface minus the derivative of the normal direction of V1 is equal to minus sigma over epsilon naught. So this becomes our second boundary condition. While the potential is continuous, if I have a surface charge density, the potential is not continuous in the first derivative, right? I would expect that in the first derivative of the potential that there would be some dependence on this charge density.